Okay. We really have to delve in this, just so that we can properly touch this, né? Over here, what we've discussed, né, is we've discussed the self-commutated var compensators, né? We've stated that it includes the VSC, which is your voltage source converters, okay, and current source converters, your CSCs and your VSCs, okay, as well as static synchronous compensators, which is your STATCOMs, né? United power flow controllers, your UPFC, and dynamic voltage restorers. Now, again, these are fancy terms. What do these terms mean? It's simple. This is what it means. The self-commutated VAR compensators, they include the VSCs and the CSCs, as well as your STATCOMs, your UPFCs, and your DVR. That's it, long story short. So when we say self-commutated VAR compensators, there's a range of them: VSCs, CSCs, UPFCs, and then your DVRs. That's it. That's all this means. Obviously, if you read it, it can be confusing, but these are just 1, 2, 3, 4, 5. Five different types of the same thing. What is the same thing? They are all self-commutated VAR compensators. Okay, right. With that being said, pay careful attention to our switching. There's line 1, there's some inductors there, there's a capacitor there, there's switch 1, somewhere there's switch 2. Let's see. Okay, right. Switch 1. Okay, right. Switch 2. Where's switch 2? Oh, there's switch 2, and then you have switch 3. Okay, switch 4, right here, same thing. Okay, now mind you, this is your VSC topology, this is your CSC topology. Now check this out. The 6 switches in the VSC and CSC topologies are realized by an IGBT with an inverse diode, okay, as shown, simply meaning those switches are in actual fact IGBTs that are being switched. Okay, right. We read about that earlier on. These things, they are switched with what we call voltage control at the gate terminal. Okay, right. So this is your converter topology realized with IGBTs and inverse parallel diodes. Okay, right. A STATCOM. Now, what is a STATCOM? A STATCOM, as we've discussed, it is a type of self-commutated VAR compensator. That's it. The same way how you have your VSCs and your CSCs, you have your STATCOMs. Okay. Now, what is a STATCOM? A STATCOM, it is a name given to either a VCS or a CSC with its advanced control included. So simply meaning we are still talking to VSCs and we are still talking to CSCs. However, in this case, when the moment you say STATCOM, how does the difference come into play? It comes into play with the effect of what we call advanced control systems that are included, or advanced control capability, which is now included. Okay, so the STATCOM, it is connected in parallel to the power system through a coupling reactor. The STATCOM, it is connected in parallel to the power system through a coupling reactor. Okay, it generates a balanced set of 3 sinusoidal voltages. It generates a balanced set of 3 sinusoidal voltages at the fundamental frequency with a controllable amplitude and phase shift angle. Okay, now here we can have a look at what is called a UPFC block diagram. Okay, a UPFC block diagram. Okay, what is a UPFC? It is a United Power Flow Controller. United Power Flow Controller. Okay, this is the block diagram. Over here we have a DVR, and this is the block diagram. Again, what is a DVR? A DVR, it is a dynamic voltage restorer. Okay, And then we will notice it's over here, the block diagram. Oh, okay. Okay, right, I'm just going to read here now. There is an analysis in the prescribed book that shows that the reactive power in a transmission line is equal to the real power if the phase angle between the sending and receiving end voltages is equal to 90 degrees, and double if the phase angle is 180. By inspecting the equations derived, an observation is made that the power flow between the sending and receiving ends can be controlled by one of the following: varying the reactance, in this case that's X, okay? Applying a variable voltage in series in the line. Applying a variable voltage. You are applying a variable, meaning the voltage can be varied, it can be changed in series in the line, okay? Then applying a shunt voltage at the midpoint of the line, okay? A shunt compensator is then introduced and the analysis repeated, showing that the reactive power and real power due to the shunt is now double at a phase angle of 180 degrees compared to the previous situation. In the next section of the prescribed book, a TCR is presented and the derivation of the reactor current equation done. Now, what is a TCR? It is a thyristor controlled reactor. What is a thyristor controlled reactor? Okay, that's what we are now going to discover here. To complete this section, we should study the TCR section in our prescribed textbooks. We are reminded that a derivation in this subject requires a control circuit and a relevant comments to introduce the mathematical process that will be followed. Okay, the purpose of the shunt reactor, it is to vary the reactive current component in the transmission line. This is done by means of phase angle control of the AC switch forming part of the TCR. Also note now, varying the reactive current is done by varying the reactance of the TCR. Since an AC wave has a positive half that reflects the negative half of the wave, the mathematical work to be done can be reduced by only considering one half. The derivation done, okay? The derivation done now. It uses a cosine function for the transmission line voltage. The last worked example in the chapter repeats the derivation but with a sinusoidal function for the transmission line voltage. Starting from the voltage current relationship of an inductor, an equation for the current is determined with a control variable, in this case alpha. Note that if alpha equals 0, then a sine wave with a peak of V max divided by WL will flow. Okay, this confirms what has been taught from the level 1 module of this qualification, namely that the current lags the voltage in an inductive circuit, and if the inductance is pure, then the angle between the current and the voltage is 90 degrees, the same as between a cosine and a sine wave. Since a thyristor can only carry forward current, okay, delaying the onset of current flow by means of alpha will cause current to flow from alpha to pi minus alpha. Okay, the current component at the frequency of the supply is the focus of our interest. This is the fundamental, meaning where n is equal to 1, and can be determined by using Fourier analysis of the reactor current due to half-wave symmetry. There are no even harmonics and no DC term. Imagine that. Okay, imagine that. Now let's continue. Fixed capacitor thyristor control reactor compensation. A fixed capacitor in parallel with a load draws current leading the voltage from the supply. A TCR in parallel to a load current, lagging the voltage from the supply, and its magnitude depends on the delay angle, which is alpha. Okay, right? Combining the fixed capacitor provides a method to cancel the reactive current drawn by the load over a range of currents. This causes the supply to only see active current, thus providing a power factor of 1. A few worked examples are done in the prescribed book by using a FC TCR as the compensator circuit, One type of problem provides the capacitor and reactor value and requests the range of currents that can be compensated for. Another type of problem, it provides the current range and requires the design calculation for the capacitor and the reactor. Yet another type, which in this case is your capacitive type and inductive type, are asking for the delay angle of a specific reactive component of the load current. Keep in mind that the compensator circuit has to cancel the load's reactive current. It therefore has to be 180 degrees out of phase. This can be done by reversing the sign of the load current reactive component. Numerical methods have to be used. Okay, now what are numerical methods? It's just a way of talking about approximations. Okay, to solve for the delay angle, make sure that you can follow the procedure shown in the worked examples, and then obviously there's some sort of activity there. Now let's jump to the conclusion. This study unit provided an overview of a flexible AC transmission system, otherwise known as FACTS. This does not mean that everything related to this topic has been covered, but the study unit will have given you a sound basic grasp of such a system and enough knowledge to further educate yourself regarding FACTS if the need arises in the future.